Alright, welcome back. That Cisco design guide was really interesting, so we're going to keep reading through that. What was interesting about it last time is we just learned about the different kinds of access layers you can have, traditional, stack-wise, or programmability. The other thing that was interesting is we learned an equation to determine how big you need your uplinks to be, and oh yeah, so it was called an oversubscription ratio. We learned about that. Yeah, and then we thought more about what kind of edge device is the most appropriate for the GNS network I'm standing up here. So I'm going to go back to the video I uploaded so I can see where I left off. Here it is. Yep, I did a blog post on the oversubscription ratio best practices. Alright, this is where I left off last. So the next kind of access layer you can have, we see at the top we've got traditional, simplified, and Cisco software defined. So I think we talked about traditional up here. I'm not sure about that, but this is simplified. Simplified uses switch stack configurations. Migrating to a switch stack is an effective, flexible, and scalable solution to expand network capacity at the access layer. The benefits of a switch stack are as follows. The switch stack behaves as a single device, characteristics and functionality of a single switch. The switch stack allows expansion of switch ports without having to manage multiple devices. Switches can be added or removed from the switch stack without affecting the overall operation of the switch stack. Depending upon the configuration of the switch stack, it can continue to transmit data even if a link or switch within the stack fails. When adding additional access layer switches in a stackable configuration, you should design the switch stack with the desired oversubscription ratio, both during normal operations and if there is a failure of a switch within the stack. So this is example oversubscription ratio with access dash layer switch stack. Oh, okay, yeah. So let's see what oversubscription ratio they're using. So they've got 48 port switches here. Got some connected into there, so I don't see the ratio that they're using. For example, let's say you deploy 4 48 port switches, each of which supports multi-gigabit line rates up to 10 gigabits on 12 access ports, 1 gigabit per second on the other 36 ports, with fixed 4 times 10 gigabit per second uplink ports. However, you decide to use only 4 10 gigabit per second uplinks spread across 2 inches in the 2 switches in the stack. This configuration will provide up to 40 gigabits per second uplink bandwidth in a MEC configuration when both switches are operational. However, you now have 192 access ports. The maximum potential bandwidth usage of the switch ports would be 48 times 10 gigabit per second equals 480 gigabit per second plus 144 times 1 gigabit per second equals 144 gigabits per second for a total 624 gigabits per second. The maximum uplink subscription ratio would be 6 to 4 to 40 or 15.6 to 1, assuming all M gig ports were operating at 10 gigabits per second and all 1 gig ports were being used. So that's I think a fair ratio in my research to find kind of what a best practice is for that oversubscription ratio. Anything higher than 20 to 1 at the access layer is not very reasonable. And if you're new to this, you've never heard of oversubscription ratios or anything before, you might be like me when I first learned about it and think, oh, well, wouldn't you want it to be 1 to 1? Wouldn't you want it to be where the uplink has more capacity available than what would ever be sent up by the access layer? Well, the answer to that is no, because you're not going to have the equipment at the access layer continually being used at the maximum rate, maxing out. So there's no reason to have the ability in the uplink to process these as if they were maxed out all the time. It's gonna it's just not necessary. So this is this is what you will typically see as some sort of oversubscription ratio that has actually allows for more bandwidth at the access layer than can be processed at the distribution layer. But when you think about it, that actually does make sense, because the access layer is never going to be just fully utilized all the time. More realistically, you may have the following actually connected to the switch: 32 Catalyst 9100 series APs operating at 5 gigabit per second connected across the stack switch, 128 Cisco IP phones and or end user devices, PCs, Macs, etc. operating at 1 gigabit per second connected across the switch stack, 32 unused ports across the switch stack for future capability. The actual potential bandwidth usage of the switch ports would be 32 times 5 gigabits per second equals 160 Gbps plus 128 times 1 Gbps equals 128 Gbps for a total 288 Gbps. Therefore, a more realistic view of the oversubscription ratio is 288 Gbps to 40 Gbps, or 7.2 to 1, which is much better than 15.6 to 1. So that means that it is possible that your uplink will receive 7.2 times more traffic than it'll be able to process. But it's unlikely that will ever occur, because things aren't going to be maxed out all the time. Again, this configuration provides for additional capacity in that you have an additional 12 times 10 Gbps unused uplinks across the switch stack, as additional devices require M gig port speeds. As devices transition to 10 Gbps speeds, and as you add additional switches in the switch stack. If one of the switches with uplinks were to fail, the number of uplinks decreases to 2 times 10 Gbps. However, the number of ports also decreases by 48 switch ports. Does it? If one of the access switches were to fail. Yeah, they weren't very clear about that. So they're talking about the access switches. If one of these access switches will fail, that is connecting to the uplink, yes, you will lose your uplinks, but you'll also no longer have these two devices. So you'll decrease your available bandwidth up to the uplinks, but you'll shrink your ratio down on both sides. However, the number of ports also decreases by 48 switch ports. In this scenario, it is important to balance the devices operating at N gig speeds and at 1 Gbps speeds across all switches to maintain a similar oversubscription ratio. For example, APs operating at 5 Gbps should be spread equally across the switches in the stack. This is already a best practice for AP high availability in a wireless deployment. Assuming all devices were equally distributed across 4 switches, in the example above, if one of the switches with uplinks were to fail, the actual oversubscription ratio would increase from approximately, it looks like they used an extra colon here instead of a dot. So what they meant to say is, as they were saying above, 7.2:1 to 10.8:1, but this is still a reasonable number. I think once it starts getting above 20, then you're just gonna need more capacity on your uplinks. Another best practice is to select switches without uplinks as the active and standby of the switch stack, as shown in the figure above. Uplinks should be provisioned on the member switches. This way, if the active switch of the stack fails, you don't have a double failure, meaning that you lose both the active switch and half your uplinks. Okay, so if you do it here, when one of your then if the active switch of your stack fails, you don't lose half your uplinks. Alright, next section is modular access switch platforms. An alternative to deploying switch stacks at the access layer is to deploy modular switch platforms such as the Catalyst 9400 series. Catalyst 9400 series 4, 7, or 10 slot models can be deployed depending on the port density requirements of your floor IDF's wiring closets. An advantage of modular platforms is that additional line cards can be added to empty slots within the chassis to increase capacity without having to worry about whether additional rack space or power, assuming sufficient power supplies are already provisioned within that chassis, exists within the IDF, which houses the modular switch. Adding an additional line card may also be less expensive than purchasing another stackable or standalone switch. Another advantage of modular platforms is that they are typically designed such that the supervisor can be upgraded to increase the performance of the platform without having to replace it. This can be a cost advantage of modular platforms over time compared to stackable platforms. Redundant supervisors can be deployed to provide chassis level high availability such as non-stop forwarding and stateful switchover, similar to the active standby functionality with a NSF/SSO stateful switchover of a switch stack. As with switch stacks, uplinks should be spread across line cards within the modular chassis. Oversubscription ratios should be determined both during normal operations and during failure scenarios. APs and end user devices should be spread across available line cards to minimize the impact of the failure of a single line card within a modular chassis. Alright, let's try to get through this. I'm kind of losing steam now. I might need to just take a break. I'm going to take a break. I'll be back soon. Alright, welcome back. This is increasing uplink speeds. As you continue to add more switches to a switch stack, you must keep in mind the distribution of the uplinks across the switches in the switch stack, and the oversubscription ratio during failures. Likewise, as you continue to add more line cards to a modular switch platform, you must keep in mind the distribution of the uplinks across the line cards and the oversubscription ratio during line card failure scenarios. Deploying multiple 10 Gbps uplinks may not be effective for larger switch stacks or modular platforms when migrating to N-gig capable switches or line cards. The maximum number of links in an Ether channel configuration is 8, resulting in a maximum uplink bandwidth of 80 Gbps. Further, this requires 10 Gbps switch ports across the distribution layer switches for each access layer switch or switch stack. Hence, it may be more optimal to migrate to higher speed links between the access layer switch or switch stack and the distribution layer switches. Alright, so here's a oversubscription ratio, and remember that oversubscribing is not a bad thing. In fact, it's bad to undersubscribe, because then you're just wasting links out there that don't need to be out there. For example, instead of deploying 4 48-port switches with a fixed 4x10 Gbps uplinks in a switch stack configuration, you may want to deploy 4 48-port switches along a 2x25 Gbps uplink module in 2 of the switches within the stack. This configuration provides up to 100 Gbps uplink bandwidth in a MEC configuration when both switches with uplinks are operational. Fewer uplink ports are required at the distribution layer stackwise virtual pair, and fewer optical fiber pairs are needed between the distribution layer stackwise virtual pair and each of the access layer switch stacks. However, when deciding to upgrade the uplink speeds between the access and distribution layer switches, you should keep in mind the following. The optical receiver modules, which connect the distribution layer switches to the access layer switch platforms, have to interoperate with each other and have to be compatible with the fiber optic building distribution cabling, multi-mode fiber MMF or single mode fiber SMF. Note, Cisco offers a gradual migration path with the support of dual rate optics, where each 25 Gbps optics can operate at both 10 Gbps and 25 Gbps speeds. With this approach, distribution layer devices can be upgraded to 25 Gbps while the access layer still operates at 10 Gbps, and the access layer switches can be upgraded over a period of time. Distances supported by multi-mode fiber typically decrease as speeds increase. This means that if you are upgrading from 10 Gbps to 25 Gbps between the distribution layer and the access layer switches, you have building distribution cabling consisting of multi-mode fiber, OM2, OM3, or OM4, You have to determine if the cabling will support the distances between the main IDF, which may house the distribution layer switches, and the floor IDFs, which may house the access layer switches at higher speeds. Keep in mind losses due to patch cables between the building distribution cabling and the actual equipment within the racks. Yeah, so my understanding of single mode fiber and multi-mode fiber, they talk about multi-mode fiber here, is, yeah, it's a distant, it's distances. So multi-mode fiber is cheaper fiber, it's the cheap stuff, but and that's because it doesn't go quite as long as single mode fiber. It's got more limited distances, and it's got more limited speeds. In addition to that, it has more limited frequencies, I believe. With a single mode fiber, not only can it go longer and have a higher bandwidth, you can do something called CWDM or DWDM, which is which requires wavelength speeds or wavelengths that are really tiny, too tiny to be supported by multi-mode. I think I might be not entirely right on that, but that's my just off the top of my head understanding of this. If this mentions it further and it turns out I was wrong, I will make sure to call that out. Note, the Cisco 10/25 G-based CSR module supports a link length of up to 300 to 400 over OM3-4 at 10 gigabits, and up to 300-400 meg over OM3-4 at 25 gigabits. So it supports a, oh, okay, well it supports the same, okay, well that's nice. It does it both the same length and the same OM, depending on the multi-mode fiber quality. It also supports link lengths of 82 meters over OM2 at 10G and up to 70 meters over OM2 at 25G. This module requires RS FEC on the host port for full reach operation at 25G. Using base R FEC, the module can support 70/100M over OM3-4, and without FEC, it can support 30/50M over OM3-4 at 25G, depending on the multi-mode fiber quality. For 10G operation, FEC is not required. If you have older multi-mode fiber, OM1, speeds above 10 Gbps may not be supported. Single mode fiber generally supports both higher transmission rates and longer distances than multi-mode fiber. I was right. Link queuing. The actual uplink oversubscription ratio that you implement between your access and distribution layer switches is dependent on your business requirements. Uplink ratios up to 20:1 between the access and distribution layer switches, where 1 is the uplink and 20 is the added together ports on the access layer, and 4:1 between the distribution layer and core switches have been implemented in networks. The higher the oversubscription ratio, the higher the probability that temporary or transient congestion of the uplink may occur if multiple devices transmit or receive simultaneously. Catalyst 9000 series switches dynamically allocate buffer space across switch ports and queues in order to optimize the utilization of the existing buffer space. However, switch buffer space is a finite quality that depends on the model of the Catalyst 9000 series switch platform, specifically the version of the UADP ASIC and the number of UADP ASICs within the switch platform. During periods of temporary congestion, the buffers on individual switch ports and queues may become exhausted, resulting in packet loss. It is recommended to implement queuing on switches, where oversubscription of ports can result in transient congestion, which can cause packet loss. Queuing ensures that when congestion occurs, your higher priority traffic, which is more susceptible to packet loss, such as voice traffic, is given preferential treatment over lower priority traffic. This preserves the quality of experience for your business critical applications, such as voice. Access layer variations. In some situations, such as for IoT and for multi-dwelling unit MDU deployments, the access layer is often augmented with additional cascaded switches. For Cisco software-defined access, described later, access extension deployments, these access devices may be extended node switches. For MDU deployments, the devices may be small distributed access switches or gigabit passive optical network, GPON, optical network termination devices. Network designs for these and other variations of the access layer are outside the scope of this guide. Access layer platforms, the preferred options for the campus wired LAN include the following Cisco switches as platforms for the access layer. So here's what you would want if you wanted a modular switch, but then now this is just the same thing, right? I guess it looks a little different. But okay, so let's take what we learned from this and pick a better access switch. In my lab, I was using an Open vSwitch, but that's just not going to be good enough for me, I think, because we're trying to simulate something you would put in a building. Open vSwitch, I learned, is a switch that you would use only for virtualization. So this is a simulation of a Juniper MX80 here. This is a simulation of a Aruba OS CX. So these are devices you can actually purchase. So let's say Juniper Junos MX80. We actually get a picture of a device that you can actually purchase and implement. So that's what we're going for. There's nothing like that for Open vSwitches because they are not meant to be actual physical devices. Okay, so let's think about that ratio. We want a ratio that is no greater than 20:1, and then a ratio of 1:1 or less is just not necessary. So let's take a look at what we've got on our Aruba OS CX boxes here. Now I'm looking for hopefully 10 gig ports. Oh, here we go. This is what I'm looking for. So I'm looking for the physical interface information because I want to see what speeds I can use in my calculation. Okay, so I think even my access layer is not going to be... but now things are getting tricky though, because this is between the access and the core. So if we're talking about connecting the edge to the access, the calculation's got to be a little bit different, because we saw the port we were using. Like, let's see here. So yeah, it's like this is quite a bit different here than what they showed up here. Yeah, so this is, yeah, I'm not even sure what this is meant to be, but this connection is quite a bit different than this connection. But that's because this is a two-tier design. So it looks like there's just options, but we want to choose just the model of switch for now. Okay, so we're going to go to switches. I guess a Cumulus VX would be interesting. Okay, so that's another virtual switch though, I believe. Oh, never mind. Actually, it looks like it's... Yeah. It's an open source switch, so you can... Okay, yeah, let's go with that, because that's used for an open source switch. So that's pretty much what we're looking for. Alright, let's see if we can get some... So if I just... It's empty. Well, I mean, if I can't get it working, obviously I can't use it. You know what? I might want to just use the Aruba. Oh, I actually just don't even have that many switches on here. I mean, I could just use like the Ethernet switch. I don't have that many devices loaded in here currently. Let's get an Arista. That actually might be it. Oh, I also have a QFX. Extreme Networks. That would be a good one. Let's go with Arista. Oh, sweet, and I've already got them all. Okay, so we'll just go with the latest one. Whoops, but unfortunately, so there aren't any where everything is ready to go. Let's see here. Oh. All right. I just had to reactivate my account. Oh, god damn it, I have to wait 5 minutes though. Okay, I guess I have to wait 5 minutes. Alright, so I guess I'm not sure what to do in these 5 minutes. Let's see if there's another one. Here's an Arista Docker container. Okay, sweet. Yeah, if it's just a Docker container, then it comes with oh shoot. That did not work at all. I wish the Cumulus would work. Oh, okay, Cumulus is working now. Oh, okay. So it actually lied. It's not what's listed there. It's just the same as the username. God, that's so annoying. You can see here it says 243M under the 24, but here they only have 5M. But up here they have 240F. Here they only have a 3M. So they're not aligning together. What about 2.3? 2.3 only has 1M. 2.2. Yeah, I don't know. I mean, I guess maybe it'll work with if I just rename it or something. Oh. Wait. Oh, this is 2.6. 2.6.0.1F. So this looks kind of like what I need. This should be 4.7.1. How big is it? Alright, let's just go with it. It's 4.3.1.0. Okay, so I guess I'll just change this 3M to 0F and maybe that'll work. I can change this to 2.5. I don't know. But that's going to take a little bit of time. I guess there's only a few seconds left. Five seconds. All right. Oh my god. Yeah, this is what I was this open source Cumulus Linux. This is what I thought was what I was talking about. So it looks like Mellanox, but these are now NVIDIA's. But it's Cumulus Linux. Cumulus VX. So it's like taken over by Mellanox, it looks like. But you can buy a Whitebox switch, I think, and then install Cumulus Linux on it. Yeah, open networking with Whitebox switches. Yeah, that's true. Troubleshooting issues is a big thing. And interoperability is a big thing too. Yeah, so it looks like NVIDIA acquired Cumulus, so it's no longer open source. Okay, that makes sense. This is 5 years ago. Yeah, I think ubiquity is, yeah, this is like the modern day answer. Yeah, I think this is the way to go for anything. Like in the home. Yeah, for home use. Yeah. Yep, this is definitely the way to go. Oh, that's like, I like those phones. Those look really good. Alright, but anyway, that's going to be the end of this video. Oh wait, is it? It's not. So I was waiting for that to upload. It's not uploading. Shoot, I don't have a switch. I guess I'll go with the Aruba then, because that's really all I got. Yeah. For some reason that didn't work when I uploaded that, so just cancel it. Yeah, I'll probably go with the Aruba for the Edge because that's the only one I've got. And then, yeah, we'll see. But, yep, that's the end of this video. Thanks for watching. See you in the next one.